All right, welcome. This is the video for section 4.5, which we will go through here. 4.5 is applications of exponential and logarithmic equations. So let's dive into it. Let's see here. So in this section, we should see probably just a bunch of word problems and problems worked out. So applications of exponential and logarithmic. Oh, I'm writing in a board that you can't see again. There we go. Okay, there we go. Functions. Okay. So one of those applications is compound interest, and we have the credit card, debit card assignment. Really kind of is in the same ballpark here. So compound interest. So we have this. The idea here is, suppose we go to your bank and you deposit let's say $10,000, nice round even number. And they give you a, let's say, 4% interest. And that's compounded yearly. What that means is if you put that $10,000 in there and leave it for 1 year, at the end of the year, they're going to come in and say, good job, we love you, we're going to give you 4% of the amount that you have in your account and put it into your account, and that now becomes yours. So after that first year, you get 4% or 0.4 multiplied by your $10,000, right? So that is $4,000, right? Right? And that's put into your account. Oh, I'm sorry, my bad. Back it up, back it up, back it up. 4%, not 40%. So that is 0.04. That's 4% times your 10,000. So you get $400 dumped into your account. So after 1 year, you now have the $10,000 that you started with plus the $400 in that account. Now, if you leave that $10,400 in another year, you're going to get that multiplied by 0.04 for the next bit of interest. That's your second year interest. All right. So we're going to take that 10,400, multiply it by 0.04 again. 10,400 times 0.04. This gives me $416 interest for the second year. So that's an additional $416. And you can see the amount that they gave you is more than the first year. So we add that into it, and the amount that I have after 2 years is the 10,400 plus 416 more. So I have $10,816 total. And then after the third year, my third year interest is always 4% of what you have. So it's 10,816 multiplied by 0.04. So I take that. That ends up being $432.64. And we add that back in, of course, to the original 10,816. And so after 3 years, I end up with $11,248.64. And now that we're in the pennies, the calculations that we do from now on will round to the nearest cent. But after 4 years, after 5 years, after 6 years, the amount that gets put into the account, as long as we leave it alone, gets greater and greater. So there's more and more interest put in the account every year. And we can express this as the amount. There's a function that describes this. The amount that's in there is the A naught. This is called A naught or A sub 0. That's the initial amount. Or sometimes you'll see it as just a P for principal. But the amount that's initially in the account multiplied by 1 plus the rate raised to the T. And this right here is your yearly compounded interest formula. Again, you might also see it as the amount after some amount of time is equal to P, where P is the principal, 1 plus R raised to the T. So it doesn't matter which one you use. A naught stands for the initial amount. P stands for the principal, which is the initial amount. So either one of those, but that's the formula that we'll use. And we can use this to figure out, rather than having to go through year 1 calculation, year 2 calculation, year 3 calculation, if we're asked how much is in the account after 15 years, rather than calculating year 1 interest and adding it, and then calculating year 2 interest and adding it, and then 3 and all the way up to 15, that's a lot of calculations. I can just plug it into this formula. The amount after 15 years is what I'm looking for, so that's A of 15, is equal to, the principal was $10,000 in this problem, and I multiply that by 1 plus 0.04 for 4%, raised to the number of years is 15. Right? This is clearly a calculator question because these can, the 1.04 to the 15 is humongous. It's not humongous, but it has a lot of decimal points, and it's horrific to do by hand. So A of 15 is equal to 10,000. This, again, just simplifies to 1.04. So I took 1.04 raised to the 15th, and I get 1.8009435055506, and there's more digits. But if you just keep this number in your calculator and then multiply it by 10,000, right? That's what I'll do. 10,000 times that, and it just moves your decimal place over. So I get the amount after 15 years is $18,009. And then my next digits are 435, so I would round that to 44 cents. And that's what I can expect to have in the account after 15 years. Now, this is not very oftenly used, this idea of yearly compounded. Sometimes it is, depending on your financial institution and what product you've got. But most financial institutions will compound monthly. And so our formula changes just a little bit for that. So monthly compounding, or in fact, let's just go in general. Let's just say other than yearly. Compounding. Because sometimes they'll compound twice a year, depending on if you're, some annuities, some life insurance type mutual funds, policies, things like that, will compound twice a year. Sometimes they'll pound quarterly, which is 4 times a year. Sometimes, if you go to those title loan companies, will compound weekly sometimes because they're horrific people. But we might see all sorts of things, right? So if you're compounding other than yearly, so for compounding end times per year, with a yearly rate, no matter what your compounding period is, typically they'll give you a yearly rate. So with a yearly rate of R, the compounding formula changes just a little bit. But it is now the amount after number of years. T is number of years, right? So compounding formula, let's say after T years is the amount as a function of T, time in years, is still equal to that initial amount that you put in. 1 plus, but here we take our R and divide it by the number of compounds there are in a year. And then when we raise it, we multiply it by the total number of compounds, which is the compounds per year multiplied by the number of years. And so we have this. And if that's hard to read, which sometimes my writing in here isn't the greatest. Oh, hello. That's not helpful. Nope. Again, in the book, they use a P, but P and A naught are the same thing. So that's just 1 plus R over N, all raised to the N over T, N times T, right? So if I'm just going to grab a problem rather than write it, and we'll talk about a bunch of different questions they can ask. Okay, so suppose we have $2,000 invested in our account. So that means right off the bat, my A naught, or if you want my P, doesn't matter which one you use, A naught or P, is $2,000. It's invested in an account earning 3% annual interest. So that R is 0.03. Convert that to a pure decimal. And is compounded monthly. So that means N is 12. N is the number of compounds that you have in a year. So if we're doing it monthly, that's 12 compounds. So we're asked 3 things here. Number 1, how much will be in the account after 6 years? So that is to say, what is A of 6? Right. But that's equal to the initial amount that I put in is $2,000 multiplied by 1 plus 0.03 divided by 12. And I raise that to N times T, so that's N is 12, and I multiply that by 6. So I can do a little bit of simplification if I like. 0.03 divided by 12 is 0.0025. And if I add that to 1, this turns into 2,000 multiplied by 1.0025. Raised to the 12 times 6 is 72. And now in your, if you've got a TI 30, you can just throw this all in one line. Be careful with it. It should look something like this. 2,000, your little star for multiplication. And then you should have 1.0025. And sometimes it'll have a caret, or sometimes if you have one with a good math print, it'll actually write it as an exponent, but to the 72. But use your calculator, do this on your calculator, see if you get the same answer. You should get, rounded to the nearest penny, $2,393. 2393 and 90 cents. Let's look at the second question they ask. How long will it take for this account to reach $3,500? Well, that's the amount that we want to figure out, the amount at whatever unknown time. But that means the amount at I don't know what time is 3,500. So I'm going to replace that into the first part of this equation. So the equation is going to look like 3,500 equals 2,000 multiplied by 1.0. It's the same information here, so I'm just going to shortcut it. My rate is the same, so 0.03 divided by 12. I'm still going to get 1.0025. But now it's multiplied by 12t, and I don't know what t is. So the whole point of this is to solve for that t. So how do I do that? Well, I want to get this to look like y equals b to the m. So I'm going to divide out this 2,000 in front of all of that. All right. So the 2,000s cancel out on the right-hand side. On the left-hand side, I get 1.75. Cancels, cancels. So I get 1.0025 raised to the 12t, which is now in this format where my m, that exponent, is just 12t. But we've seen what to do with this. I'm going to take the log, either the natural log or the log base 10. It doesn't really matter, but I'll take the log of both sides. So I'll just do ln of 1.75 is equal to ln of 1.0025 raised to the 12t. And again, I specifically did that so that this exponent inside the natural log can come out in front as a multiplier. So I get 12t multiplied by the natural log of 1.0025. Now again, this natural log of 1.0025 is just some number. I don't know what it is. It's just a number. But that means 12 multiplied by that thing is just a number. And I can divide both of those out. So I will. I'm going to divide from the right-hand side, 12 times the natural log of 1.0025. And on the left, I'll divide out 12 times the natural log of 1.0025. The natural logs cancel out. The 12 cancels out. That isolates just a t on the right-hand side. And on the left-hand side, our exact value is the natural log of 1.75 divided by 12 times the natural log of 1.0025. Which is great to have an exact answer, but what does that mean to me? If somebody came to me and said, hey, this is the amount of time that you need to put your money in this account, is the natural log of 1.75 over 12 natural log of 1.0025. Super, super helpful, right? Not so much, but I can evaluate that to get an approximate amount of time. So again, try this in your calculator. I put it in and I got, I guess I could probably cheat. This is from the book. But I plugged it in and I got that T is approximately 18.7 years. Oh my gosh, you suck. 18.7 years. I got 18.6772. Right? So that's about how long we should keep it in there. So if you wanted to make more than $3,500, maybe plan on not touching it for, 19 years, something like that. Okay, and let's look at the third thing they ask, how long will it take for this thing to double in value? Well, that means that we're looking for $4,000, right? So in this, A of t equals A1 plus r over n to the nt. A of t is 4,000. I don't know what t is because I'm trying to solve for that. So the initial amount, though, I knew was $2,000. 1 plus my 0.03 over 12, which again, this whole thing is not going to change. That's still 1.0025. This is raised to the 12 because that's how many times we're compounding. And again, we're searching for t. So I'm going to divide each side by 2,000 right off the get-go to get the number in front of my exponent out of there. That gives me 2, which shouldn't surprise us because we're trying to double this thing. So the 1 plus 0.03 over 12 simplifies again to 1.0025 raised to the 12t. And we'll go through the same process that we just did. So take the natural log of each side. Natural log of 2 equals the natural log of 1.0025 to the 12t. That 12t comes down as a multiplier. And then I divide each side by 12, natural log of 1.0025. Again, because the natural log is going to cancel the natural log, the 12 is going to cancel the 12 and isolate my t. And that's the amount of time that it's going to take for this thing to double. Over on the left-hand side, I also have to divide this by 12, natural log of 1.0025. So putting it in the calculator, and again, if you're trying to throw it all in at once, be careful. The answer that I get here is about 23.13 years, or about 23.1 years, right? If you get something like 0.00014425, this answer is wrong. Your calculator misread what you typed in because you went natural log of 2 divided by 12 and then times the natural log of 1.0025, right? And your calculator thought you meant natural log of 2 divided by 12 and then take that result and multiply it by that natural log. So if you're going to type it in one line, make sure you're putting parentheses around that whole denominator so it doesn't treat it like the order of operations would as you go left to right. That parentheses is your entire denominator. It's so not helpful. All right. Suppose we want to invest $10,000. So right from the get-go, I've got some information coming at me. The amount that I start with is $10,000. Or if you like the P, doesn't matter which one you use, that's $10,000. Oh, we want $15,000 in 8 years. So that is to say, A of 8, we want to be 15,000. What interest rate compounded annually must we? So what compounded annually means that n is 1. And if I use n as 1, that I get that previous equation that we gave for the annual compounded interest. How much of a rate do we need to make this happen? So in that equation, it simplifies down to here because n is 1. So r over n is 1, and n times t is just t. So it simplifies, again, to the annually compounded interest formula. And I just have to plug stuff in. It's $15,000 that I want. It's 10,000 that I started with. I don't know what my rate is. That's what I'm looking for, but I want this to happen in 8 years. And so I'm now solving for R. So I'm going to divide each side by 10,000. I get 1.5 on the left is equal to 1 plus R all raised to the 8 power. But I don't need to take the log here. And I don't need to do that because my power does not have an unknown in it. So what I do instead is I'm going to take the 8th root. So I'm going to take the 8th root of 1.5 and the 8th root of the entire right-hand side. The 8th root of an 8 power cancels, so I just get this 1 plus R on the right. And to take the 8th root, you have two choices. Let me grab where's that picture I got before? All right, on your calculator, you do have this power button right here. And you can use a fraction, right? The 8th root is the 1/8 power. So if I type this in, I should get 1.5. Use that little caret. And then I'm just going to throw into parentheses 1/8, and that's the 8th root, right? Give it a try. You should end up with I get 1.05, I can't write, 1.051990. And it goes on more and more, but we'll cut it off there. There's plenty. And all I have to do now is subtract 1 from both sides, and I get 0.051990 is equal to R. That's R as a decimal. So if I want to answer the question, what rate do I need? I need to move that over 2 decimal places to get 5.199-ish %. Or somewhere around, if we're going to round it to the nearest 1/10 of a percent, we would say 5.2% would be good. Now, a couple of weeks ago, I talked about this formula. And if you don't remember it, that is fine. But if I go 1/1 to the end, all raised to the n. If you remember this. If you don't, that's fine as well. But if I let this thing run off to infinity, right? We said that this thing becomes E. And so you can see that happening here. If I have this P multiplied by 1 plus R over N to the RT, or sorry, not to the RT, but to the NT, I have that kind of built in there, right? But the R kind of becomes a little bit less significant inside the parentheses as so much as the n runs off to infinity. And so this thing, if we compounded yearly, we would get some certain amount of interest once a year. If we compound twice a year, we get a little bit more interest because halfway through the year, I add half the interest, but on the second half of the year, when I go to calculate that interest, I get interest on the first part of the year's interest that was given to me. And so I get a little bit more if I compound 2 times a year. And if I compound 12 times a year, I'm going to get even more than that, but it's not a ton. And so the question was, how far can we go with this? Can I compound so many times? Can I compound every second? Can I compound 8,000 times a second? What's the limit of where this thing can go to compound as much as possible, right? And so what we end up having here is that as we let 1 plus R over N to the N, as N runs off to infinity here, this R kind of makes a jump out. This thing ends up being E to the R. You don't really need to know this. You won't be asked to recreate this, but mathematically, that's what happens. And so in the formula, AT equals, let's go with P 1 plus R over N to the NT. Right. As we say, well, let's let N go crazy. Let's just say I'm going to compound this so many times that you can't even blink without compounding a bajillion times, right? And what happens is all of this junk, this 1 plus R over N all to the N, this 1 plus R over N all to the N turns into an E to the R. And so then this thing turns into A of T equals P E to the R, and it's still all raised to the T as well, so it's T in the exponent. And this is called continuously compounding. Which I've never seen an account actually do this. I've worked in finance myself every once in a while. I bailed out because I didn't like it, but I mean, if there's anyone that's seen an account, let me know, because I've never seen it. But theoretically, this is what would happen if you just said, you know what, let's compound this all the time. So in between any 2 moments in time, there's basically an infinite number of compounds. And it doesn't go crazy. You're not given an infinite number of, an infinite amount of interest. It's limited by that E to the R. And so we can do calculations with this. And we can say, or it can be asked this. Suppose you invest your newly acquired bonus of $4,000. So A naught is $4,000 into a requirement account that promises a minimum of 5% interest. So R is 0.05. It does say minimum, but we're going to run with that minimum. And it's compounded continuously, so that tells us that we're using the A of t equals P times e to the RT. Or if you like, A of t is equal to A naught e to the RT, whichever one of those you like. It doesn't matter. I don't care. They're both the same thing. So how long will it take to triple in value? So that means that the amount after I don't know how long should be triple that. So $12,000, right? So I just plug those in. $12,000 in place of A of t. A naught is 4,000. E to the R, which is 0.05 times t. I start by dividing 4,000 to isolate my exponent. Not a surprise that I end up with 3 because I want to triple my value. But when this t is up in the exponent, that's your cue to take the logarithm of each side. And since e is my base here, I really, really want to take the natural log of each side because stuff will simplify nicely. So I do. Natural log of 3 is equal to the natural log of e to the 0.05t. That 0.05t comes down as a multiplier, so I have natural log of 3 is 0.05t times the natural log of e, but the natural log of e is 1. So that is the natural log of 3 is equal to 0.05t, and so I just divide each side by 0.05. And I get t is equal to the natural log of 3 divided by 0.05, or calculating that to something that's useful to us, I get 21 point, about 22 years. And that's how long we take to triple. So again, just kind of logistically speaking here, if you threw $4,000 into an account 22 years later and pulled out $12,000, that might not be a great use of your time and money. But if you had an extra $1 million laying around and you threw it in there, and then 22 years later came back and said, oh, it's time for my kids to go to college, and you had $3 million to put them through college, that might be a little bit more meaningful, right? Okay. Another application is exponential growth and decay. So let's talk about exponential growth. Exponential growth, you see things in things like biological models, bacteria growth, population of animals growth, human population growth, all sorts of things. So exponential growth. And exponential growth simply is a continuously compounded function. So that is to say, the amount of whatever it is at some time is equal to that initial amount multiplied by e to the k times t, with k being some sort of some growth constant. It's a growth rate constant. Right? If k is greater than 0, then we have growth. Exponential decay is the same thing. Exponential decay is seen in things like rotting flesh stuff. That's gross, but like decay in the forests, things like that. But also in like radioactive decay and things like that. So exponential decay is the same formula, A of t is equal to A naught e to the kt. The only difference is that k is less than 0. So if you have a negative rate, it's a decay. If you have a positive rate, it's growth. Exponential decay is also notable in like the value of something that's used, like machines. The more they get used, the less valuable they become, things like that. So let's take a look at an example. All right, so this is like on 2 pages here, so it's all one question. But in order to perform atherosclerosis research, epithelial cells are harvested from the discarded umbilical tissue and grown in the laboratory. A technician observes that a culture of 12,000 cells grows to 5 million cells in 1 week, right? So I'm just going to note some things as I'm reading this. A technician observes that a culture of 12,000 cells we started with 12,000. It grew to 5 million. So 5 million is the amount after 12 weeks. And since I'm doing A of 12, T is in weeks now. Okay. Assuming that the cells grow exponentially, that tells us that our formula is A of T equals A naught e to the kt, where k is simply going to be positive, right? Find a formula for the number of cells in thousands after T days. Oh, that sucks. Oh, just kidding. 12. I don't know where I got 12 from. Where did I get 12 from? But this happens in 1 week, so I'm going to erase this. It's not A of 12. It's going to be A of 7. And T is now in days. Also, make sure you can read English, which is apparently difficult for me. But here we are. So A of 7, 7 days, we've got 5 million. I want to figure out what the equation is. The only thing that I really need for the equation is to figure out what k is. T is just going to be a variable. A naught I know, and those are the only 2 things that I wouldn't know on the right-hand side. So I'm going to plug in what I know here, and that is that 5 million for A naught equals 12,000, or sorry, 5 million for A of T equals 12,000 for A naught e to the k, and time was 7, so times 7. Okay. So the first thing I'll do is divide each side by 12,000. All right, so 1, 2, 3, that's 5,000 divided by 12. Ugh, 416 point, I'm going to round this to like 6, 7, equals e to the 7k. K times 7 is the same as 7k. And then I'll natural log each side. Natural log of 416.67 equals the natural log of e to the 7k. The 7k comes forward, so I have 7k times the natural log of e. But again, that natural log of e is just 1. So this is just 7k on the right. And on the left, this natural log of 416.67. And divide each side by 7 to find k. So I'm going to round this because this k is going to have a ridiculous amount of decimal points. So I'm going to say natural log of 416.67 divided by 7. And I get 0.86. 1756. We don't really need this many, so I would say, I think the questioner would say round this to some number of decimal points. So let's round it to 3. So this would be 0.862-ish. And we have our k, which means that our function is the original amount, which was 12,000, e to the 0.862 times t, and that's our function. So let's look at a decay problem here. We have iodine isotope 131. So iodine 131 is commonly used radioactive isotope that helps detect how well the thyroid is functioning. Iodine 131 decays exponentially, and after approximately 8 days, only 1/2 of the original amount remains. If 5 grams of iodine 131 is present initially, find a function that gives the amount of iodine 131 in grams t days later. So gathering what I know or what I have from the information given to me, 8 days, 1/2 of the original amount remains. So what does that mean? After t equals 8, the amount that I have, the amount at 8 days, is 1/2 of the amount that I initially started. Right? And that's all I need to figure out this problem, right? I don't have to have an amount because it doesn't matter how much I started with. After 8 days, I have 1/2 that amount. So in this problem, a of t equals a naught e to the kt. The amount after 8 days, I'm going to plug in 1/2 a naught equals a naught. I don't know how much I have, but again, it doesn't matter. I'll show you why in the next step here. You can probably see why. But this happens after 8 days, so I'm going to plug in 8 for t. So if I divide each side by a naught, the a naughts all cancel out, and it didn't matter how much I started with. The question's always going to boil down to, with a half-life problem, as 1/2 equals e to the 8k. And then I just natural log each side. So I get the natural log of 1/2 equals the natural log of e to the 8k. The 8k moves out in front. Natural log of e is just 1. We get the natural log of 1/2 is equal to 8k. And I divide by 8. So this then is k is equal to the natural log of 1/2, which is like negative 0.693. Divide that by 8, and I have my k. So I get k is approximately negative 0.08664, which again, it'll tell you in your problems where to round these. It should, and if it doesn't, then just throw it out to 5 digits or so. But then to answer the question was to build the equation. So that equation is that original a of t is equal to a naught, which I don't know what that a naught is. So I'm just going to plug in a naught because I don't have an initial number. And so, well, all right. My bad. I'm going to scooch back up to the problem. If 5 grams of iodine is present initially, I didn't need that number to do this problem, but I will put it in because it's part of the situation. That is my A naught, e to the negative 0.08664 t, and that's it. That's my equation. Okay. So you then might be asked a follow-up question. Now that we have this, we might say, if we started with 5 grams of iodine 131, how long will it take until it decays to, let's say, 1 gram? And we just plug this into the equation that we created. The amount at time t, which I don't know what t is, but that amount after that time is 1, equals 5e to the, I know this k is 0.08664 t. And so if I divide each side by 5, I get 0.2 is equal to e to the negative 0.8664 t. And then I take the natural log of each side. Natural log of 0.2 is equal to the natural log of e to the negative 0.8664 t. This whole exponent, the negative 0.8664 t. I'm missing a 0 in there, aren't I? I am. 0.0. That whole thing comes down as a multiplier. And so this becomes natural log of 0.2 equals negative 0.08664 t. Natural log of e, but that natural log of e is 1. So if I divide each side by negative 0.08664, I've isolated t on the right-hand side, and then on the left-hand side, my final solution is about 18.6. And the original question was, t was in days based on the question itself. And so I should be down to 1 gram after 18.6 days. All right. There are other exponential examples. So let's take a look at an astronomical one. All right. In 1619, Kepler discovered the relationship of log of t equals 1.5 times the log of d minus 2.95 is the relationship between the period t in Earth years of a planet and its average distance d in millions of miles from the sun. So the first thing they ask us to do is to solve this equation for t. So with this log t equals 1.5 log d minus 2.95. To isolate the t, all I have to do is take everything raised to the 10th power. So 10 raised to that power and 10 raised to that power. 10 raised to the log base 10 of t is just t. And 10 to the difference here is like taking 10 raised to the 1.5 log of d and multiplying it by 10 raised to the negative 2.95. So I'm going to simplify this a little bit. In this log, in the exponent here, I'm going to take the 1.5 and move it up as an exponent. And then this 10 to the negative 2.95 is just some number that I can evaluate in my calculator. So to simplify this, I end up with t equals, this is 10 to the log d to the 1.5 power times, and then this 10 to the negative 2.95 is a little bit ugly. It's 0.00112202, and that just goes on. For this 10 to the log base 10 of d to the 1.5 simplifies further because it's 10 raised to the log base 10, so it just simplifies down to d to the 1.5 power, multiplied by that 10 to the negative 2.5, or this 0.00112202. So that's fine. Or if you don't want to put that 0.001122 garbage, you can also write t equals 10 to the negative 2.95 and just leave it like that, times d to the 1.5. Either one of these is fine. Okay. And then they ask us after that, we want to find the period of the planet Uranus with an average distance of 1783 millions, where d is in millions, so d is 1783. And so we just plug in the period of Uranus should be 10 to the negative 2.95 multiplied by that d is 1783 raised to the 1.5. And if I just plug all of this in, I get about 84.5 years. 84.5 Earth years. Yeah. So there's a lot of different applications of these things. There's other things, temperatures, there's earthquake models. But if you know how to play around with the logarithms and exponents and the rules with them, you can typically mess around with any of those without much difficulty. So play with those, and then by the end of this, or by the end of the first half of this video, the credit card project shouldn't be terribly difficult. But again, let me know if you have questions. Thanks for hanging out, and see you on the next one.